that over there so it doesn't bug you guys. Okay. So this is called, and hopefully today we might have time to like show you why the product rule works or where the derivative of sine comes from. So I think we should have time to at least do one of those. Okay. I know you're all dying to see that, so I'm ready to show it. Okay. All right, so section 2.5, we're going to spend 2 days. Section 2.5, part 1. Chain rule. Chain rule. And the reason it's called chain is because you had to do a derivative inside a derivative. And sometimes, today we're just going to see 2, but sometime, I don't know if it's in this class or Calc 2, we at least do it 3 times. I think there's an extra credit in Calc 2 where you do it 4 times. And that's where you really get that word chain rule. But even still, one kind of inside of another. So it's kind of like a looping thing. And that's why they call it the chain rule. Okay, so let's look at an example. Y equals x to the 3rd. We'll write some stuff down and then we'll kind of come back to this, but let's have something to look at. Y equals x to the 3rd minus 1 to the 10th power. Can we kind of even see right now how there's something inside of something else? Do we see how normally this would have just been our problem? Okay. Now we've got that quantity to the 10th power. So what I like to do is call this inside here a capital Q standing for quantity. I should have printed that, but quantity. So that's the capital Q. So in this problem, it would be x to the 3rd minus 1. Maybe we'll even do it and then we'll write something down. I think that might help too. So when we're writing something down, it'll give us a little bit of direction. So what we actually do is we change this. We take this whole thing and we just make it a big Q. Well, now, can I take the derivative of that? Better say yes. All right, how do we do that? Roll it down, subtract 1, right? So now we do 10 Q to the 9th. But the new part is, after that, you have to take the derivative of Q. And it's multiplication. It's always multiplication times the derivative of Q. So what is the derivative of Q? 3x squared, right? And the 1 then goes away. So it is then, we could even write it, let's just write it right here. The derivative of Q, or we could even do this. The derivative of Q, let's write it up here. Derivative of Q is 3x squared. If you have a quantity, you take the derivative on that quantity, and then you take the derivative of the quantity. Does that make sense? Should I say that again? If you have a quantity, you take the derivative on the quantity, and then it's times the derivative of the quantity. Okay. And then this is my answer. I just replace it back. So I need to, so now I can do derivative. We can even put, let's put the derivative here because we started it. So that would be okay to put the derivative sign already there. This is the derivative. Now we just have to fill the stuff in. So that's okay to say that this line is already the derivative. And then our answer is 10, but not Q, x to the 3rd minus 1. Don't forget to the 9th. And then times the, oops, why do I keep forgetting them? This is important. This is the derivative of Q. And that's what it's calling for here, the derivative of Q, which is 3x squared. And then the only thing here we could do is multiply these guys together. So the best answer, I think I can squeeze it on. The best answer is 30x squared, and then x to the 3rd minus 1 to the 9th. Yeah, make sure this is important. This is the derivative. We did it, but I didn't mark it. Okay, so let's write this. How are we going to write the chain rule? Let's write it again. Let's write chain rule. Q is your quantity. Let's write it like this. You're going to do the derivative on Q and then times the derivative of Q. Remember, and this notation comes up a little bit later. I think it might be chapter 3. But remember, this top just says what you're taking the derivative of, and then this is the variable that you're taking the derivative of. So we're taking the derivative on the letter Q. Most of the time, yeah, let's do that. Let's see if this makes sense. Like, let's say I just have, you can just watch if you want, but y equals, let's say, 3x to the 4th plus 2x. We haven't used this notation a lot, but it might help to see it every once in a while. See if this makes sense. We're doing the derivative on the function y. So we write dy, but what letter are we actually performing it on? We're actually rolling down subtract 1 on the letter x. And so that's why we write dy dx. This is the letter, this bottom one is the letter that we're actually doing the derivative with. Okay? And then this top one just kind of names it. So again, if we don't have anything to really name it because it's more of a function, we usually don't write this. We could, but I don't know why, we usually don't. A lot of times if we want to write that, then we just go general. We just do a D, and then but we always put the letter that we're actually performing the derivative on. Okay, does that make any sense? Just kind of notation. Okay, let's try another one. Well, let's actually put directions if we haven't done that. Find the derivative. Find the, oops. Oh. Let's start over. Find the derivative. And again, it might be what might it be on your homework? Differentiate, same thing. Okay. Okay, let's do h of x equals 5x to the 3rd minus 2x plus 8 to the 5th power. Even with last year, I had a kid who was really struggling with this. And then he finally said, well, the quantities are parentheses, right? And so I just always take the derivative thinking of the parentheses as one thing, and then I take the derivative of the parenthesis. And I'm like, yes, that's it. Quantities have to go almost always. We'll see one today where it doesn't have to, but I would say 99% of the time, quantities have to be in parentheses. That's kind of what makes it a quantity. It makes it a group. So look for those parentheses. That's going to kind of give it away that you're going to have to take the derivative of what's inside. So it's up to you how much you want to write on this. Let's write it one more time. Let's write, what would our Q be? It would be literally that polynomial inside the parentheses. That kid was totally right. 5x to the 3rd minus 2x plus 8. Okay, so now we're really looking at the derivative of this guy. Do we see how everything inside here just all becomes the Q, and now we really just have Q to the 5th. So we're going to perform the derivative on that guy. 5q to the 4th. But as soon as we have a quantity, what do we have to do? Take it times the derivative of the quantity, times the derivative of the quantity. And then it's just a matter, we can even say this is already the derivative of h. It just has the wrong letters in it, but we'll fix that, right? All right, and then let's go here. What's the derivative of q? 15x squared, roll it down, subtract 1. Roll it down, subtract 1, that goes to -2. And then the 8 goes to 0. And then we've got it all listed here. So now let's just rewrite it one more time. 5, and then q was this whole guy. Don't forget, just don't forget this exponent of 4. And then times this, you want to put that in parentheses as well. 15x squared minus 2. You don't have to take its derivative. Okay? There is a time when you have to do that, but not this situation. Once you take the derivative, because I don't have, well, let's say this. Does this make sense? How do I know when I have to do it again or not? Do I have parentheses here? No, nothing's a quantity. Okay? Nothing inside here is a quantity. I do each term and I'm done. What do we think? Today it's not going to get too much harder. Let's just talk about it. It can look a little different. Then we got to add trig, right? When in doubt, make it harder with trig. All right, y equals 1 over, so it's a fraction, 10x to the 4th minus 3x squared, and then this to the 8th power. Now, when I see fraction, what should I think? Quotient rule, good, but we don't have to do that here. Yeah, okay, so don't get too far. We don't have to. We could. I think we can make it a little bit easier. It would not be completely wrong to do quotient rule. It's just going to be a little bit longer. How can I, look at the way this problem is set up. How could I get rid of the fraction? Because this whole thing, and especially because the numerator is 1, so I can kind of get rid of that if I slide something up, and I can slide this whole thing up and make it a -8. So this is still y equals. We're going to bring it to the top, but make it a -8. So there's 2 problems on the homework. One starts out like this, and then the other one is like this, where you just have to bring it up. If you wanted to see the quotient rule, you could, but like I said, usually it's a little bit harder. I think we do stuff more like that tomorrow or Monday. When you have a quantity with an exponent, the quotient rule gets it's a little bit harder. So save that for Monday. All right, what's our quantity? There's parentheses. Well, maybe we should even start with that. There's parentheses, so that's a good indication that I have a quantity, okay? And then the quantity is the stuff inside. The parentheses kind of makes it a quantity. Here's your group that you're looking at, people. All right, so 10x to the 4th minus 3x squared. So now I'm going to replace all that with a q. I'm going to replace all that, and now I just have q to the -8. So now, can I perform the derivative on that guy? Yes, right? Roll it down, subtract 1, just take your time. So when we roll it down -8, we can actually let's put this as our official derivative. Roll it down, just take your time. What happens when you subtract 1? It actually goes to -9. And then the other part is when you're dealing with a quantity, you have to take it times the derivative of the quantity. So we can do that up here. Derivative, make sure I mark it. Derivative is, and then just roll it down, subtract 1. So 40x to the third minus 6x. And then we're ready to go. Really, we've done the derivative. The only thing is we have to, if it started with x's, it has to end with x's. So we just have to replace that. -8, parenthesis, what was our q? That quantity, 10x to the fourth minus 3x squared. And then don't forget the -9. And then our new guy, the derivative, 40x to the third minus 6x. And that answer's fine. The only thing we could do, what could we do? Because this is negative, we could bring it back into the denominator. Whatever you feel like typing is fine with me. That answer is fine. To be honest, I actually kind of like that better too. Maybe because it started with a fraction, but let's just see it the other way. 40x to the third minus 6x. Do we see how now these two are left on top, so we can just push those together, and then we can bring this middle one down. What happens when I bring it down? The exponent now is a positive number. And notice the stuff inside just stays. I'm just sliding that piece up and down. All I care about is that outer exponent. Okay. Good. All right. This next one's going to be the same, but it looks different. So the first thing we're going to do is make it like this. I'm okay either answer though, so don't feel. Sometimes in math we like negative exponents, but then in higher math sometimes we just leave it. So we're not as consistent. I'm sure there's a rule when to and not to. But. All right, so y equals the square root of x squared plus 1. So okay, and then this one doesn't have parentheses. But what's the first thing we do with square roots anyways? Change them so that they are an exponent. Right? We don't like square roots anyways. So, and what happens as soon as I change it? What am I going to have to use? Parentheses. Yeah, I'm going to have to change this to parenthesis x squared plus 1 to the 1/2. So it looked different. It was a square root, but the first thing I did was put parentheses around it and made it an exponent. And so now we're good to go. Don't let the 1/2, just work it through with a fraction. What is the quantity? The stuff now in the parentheses, right? X squared plus 1. We could even go, should we do it right away? We know we're going to use its derivative. Derivative of x squared is 2x, and then the derivative of 1 goes away. All right, okay, so let's set this up though. This is now what? This is still be y equals. This in here all becomes capital Q to the 1/2. Roll it down, subtract 1. This we'll officially call this our derivative. Roll it down, subtract 1. Just take your time. 1/2 minus 1, negative 1/2. And then don't just forget, anytime you have a quantity, you have to take it times the derivative of the quantity. All right, so now let's plug it in. Derivative equals 1/2. Q, which was x squared plus 1 to the negative 1/2. And then the derivative of Q is 2x. Not a bad answer. What can we do here though? This one, there's probably one thing we should do. Yeah, yes, beautiful, right. So this 2 can cancel with this 2. It looks a little funny, but let's even wait. Let's see if, I mean, if you canceled it now, I don't know, do we see it? Here was the other thing I was going to do to see if we could see it better. I was going to kind of leave, okay, the 2x would go on top. And then this 2 is on the bottom. And now since I'm making a fraction, if I want to move this back, I could. I could do x squared plus 1 to the 1/2. But yeah, right here is actually, maybe it is better to see. This 2 cancels with that 2. Or let's say if you didn't know that they cancel, it just like didn't click, just take 1/2 times 2. And that'll give you 1, right? So maybe even if these didn't cancel, these out here, we could definitely still multiply them together. And in that process, then they would just cancel. Okay, so here, we would cancel here. If you see it better there, that's fine. So my answer is derivative x over, and I could do the 1/2 power, absolutely, or I could bring back in the square root. Either one is completely fine. Okay, what does this find us? Why do we do this? I'm making you? Yes, no. What is this going to find us? You're going to say this in your sleep. You better say it. Slope. Yeah, it finds a slope, right? On this, and this is a doable equation, right? This is something pretty straightforward. But to find slope, it's a little bit maybe more intense. Not too bad, but this will give a slope at any point on that original graph. And then remember, slope is like rate, and that's kind of where then they take it and use it in physics. That's what was coming up. They said, I want the rate at this one point on this curve, and that's where they started diving in and coming up with calculus. Lucky us. Who asked that question, right? All right. Okay, let's make it a little bit harder. Well, hopefully it's not harder, but trig always intimidates people. So we got 4 more problems. Okay, y equals sine of x squared. But remember, we actually kind of write it like this. Sine of x squared. That's how we would read it, but that's kind of how we write it. And this would be another problem where we don't have parentheses. But what does this mean? This means how we say it, right? This means sine of x squared. And there's our parentheses. This is one time where even though it's written like this, I'll still write it like this if I have to take the derivative. Because it's so much easier to see now. Now, if you can do it without the Q, go for it. Like if you say, hey, I know I can just roll this down, subtract 1, and then take the derivative of what's inside, that's fine. Well, let's at least do it for today. We'll do Q's. We'll see tomorrow. Sometimes the Q gets it over, almost like makes it too messy, but we can definitely do it for today. What's the Q for today? Sine, right? The Q for today is sine. We could even, should we do the derivative of that right away? Derivative of sine is cosine. Okay, so now we're going to go back here, though. We replace sine. What are we replacing sine with? The Q, the quantity. It's a quantity. And now we can take that derivative. Roll it down, subtract 1, so 2Q. And then don't forget to take it times the derivative of the quantity. All right, so then we're good. Derivative of y equals 2. Q is sine of x. And the derivative is cosine of x. That's it. Okay, compare that one to, are we ready for another one? Should we stop? Are we okay on that? Okay. That seems too easy at this time, right? It's supposed to be harder. Okay. Actually, let's see. I'm going to try to, should I flip this around? Try to save some paper. Okay, good. All right, compare that one though to this one. Y equals sine of x squared. And those two don't mean the same thing. Look at the last problem. You see if it's sine squared, the 2 goes in the middle. If I want to square the x, then I have to go right with the x. And it's actually kind of nice because And WebAssign forces us to put parentheses here. Sometimes I will admit, sometimes I get lazy and I do just write it like this. But we probably should have those parentheses there. So that means what is our quantity? Our quantity then is the x squared. All right, and then its derivative is, if we're doing the derivative on q, that is 2x. And then this will change. We'll actually take, this will still be y equals because we're going to change it to a q, right? So this is going to be sine of q. Stop for that. The sine still stays there, and q was just the x squared. So it's actually going to be sine of q. All right, so that's still y. So now the derivative of sine is cosine of q, but then I have to take it times the derivative of q. So it is cosine of x squared, and then times the derivative of q, which is 2x. So just replace them. Once you've taken the derivative with all those q's, then just find your q, put that back in, find your derivative, put that back in. That's it. The only thing, maybe I would write that first, but that's fine. I mean, you could just write 2x first and then cosine. Again, if I get lazy and don't put parentheses. So is anyone thinking, like, why don't I do that? If you let this be a quantity, you can just sit and think if you want. If I let whatever is after sine be a quantity, why wouldn't I do that if it was just sine of x? Like, how do I know? Yeah, it is just an x, but how come? Well, let's say I let q be x. What is its derivative? 1. And so when I take it times the derivative, it doesn't really matter, right? Because I would be taking it times 1. So if it's really basic, if it's just x, I don't have to do this. But anything besides x, I need to think of it as a quantity. Okay. What about this one? Y equals, let's do a cosine, but a parenthesis, 7x squared plus x. So if it's not just a regular x, anything after cosine, if it's not a regular x, I have to think of it as a quantity. So my quantity then is the 7x squared plus x. But the nice thing is it'll be in parentheses. Well, like except that exception. Like if it's just cubed, sometimes then I forget to put the parentheses. But. All right, and then its derivative. How we doing? Are we okay? All right, its derivative, roll it down, subtract 1, so 14x. Don't forget about this guy. What's the derivative of x? 1, but remember you need to write it, so it's got to be plus 1. Good. All right, so now let's go back and look at what is this going to look like. We're still going to write y equals. What is that going to look like? This whole thing is one amount or one quantity. You can do A for amount or one quantity. So cosine of q. That whole thing now is just put it all together as 1. Don't separate it at all. Okay, so now we're ready to do the derivative. Derivative of cosine is negative sine. And then when you got a q, you just take it independently times the derivative of q. And that's it. Now we just have to push back to x's because the original problem had x's. So derivative, let's go up. Okay, so negative sine of q, and that goes back into the parentheses, and then times the derivative, 14x plus 1. That answer is more than fine. Sometimes we move this. This doesn't really have anything to do with the sign. So sometimes we would move that and write negative and then the 14x plus 1 and then the sign. So, and to not lose that negative, usually we always keep that first. But I mean, that's just preference. If you don't want to lose that negative, you could also distribute, but it would just be negative 14x minus 1. But you'd still need the parentheses to show that quantity times the sign. So all three of those are fine. All three of those are fine. Even if you distribute, you have to show that it's this group times the sign. So you would still need the parentheses. Okay, let's do this last one, but let's, I don't know why. Okay, let's look at last one. Or should I leave this up? Do we get those three? If you want to write all three, you definitely don't have to. Just even visually see them. Any three or any one, it's okay. Three are, you have to write them all. Okay, last one, here we go. Y equals tangent, parenthesis, 3x to the 50th. I got the book on wall, I think maybe it is 2. They like to use big exponents, but I think there's like 100. Don't let that bother you. You're still gonna roll it down, subtract 1. Okay. All right, so but anything after tangent, unless it's a regular x, you have to think of that as a quantity. Okay, so quantity, and it's nice that they put in parentheses, is the 30x to the 50th. You can do it whenever, but always know as soon as you move something to a quantity, you are going to always have to involve its derivative. Okay, so roll it down. What do we get? 150 x to the, and then just subtract 1, so 49. Okay, and then we changed all of this to a q, so now I can write it as tangent of q. And then we're ready to take the derivative of tangent is, do we remember? Remember, this one you only have to look up. It is secant squared. Secant squared. And then times the derivative of q. Okay, and then the derivative is secant squared of q, which was the 30x to the 50th, and then times the derivative, 150x to the 40th. And then same thing, we could move this to the front if we wanted to, but we would still have to pretty much write everything, 150x to the 49th, and then it would still be secant squared, and we still really should use the parentheses there. But sometimes we put the number first. Good, okay. Okay, let's look at one thing. Maybe we won't do the proof today, but I want to show you, let me see if I want to show you two things. I'm going to do a new share of this guy. All right, it's kind of hard to see, but this goes back to the very first day. Can you guys see like this pointer? Yeah, you can kind of see. Picture the red dot and, I don't know, is it blue or purple? We'll go with blue. The red and blue dot. That would be the slope if we just did it the old-fashioned way. Take 2 points and find the slope, right? But our goal is to get the slope at this 1 point. So what did we say we did? We're going to move this point closer and closer, or remember, we want the h value to go to 0. So see how I can slide this? See now how we're calculating, and this over here is calculating the slope using this. And this is calculating the slope literally using the 2 points. You see how as I get closer and closer, that blue line is still just the slope with using 2 points. But do you see how that H gets closer and closer? See how they start to be, and like right, I mean like right here, right? They're so close. So if that helps you visually, I didn't want to move that. Hang on, I was moving the red one. Okay. Does that kind of help? Remember, we said, if you look in your notes, we had a parabola and we had like 2 points, and then we talked about how H comes closer and closer, and that's what we're doing there. You can see we're doing 2 points. Remember, all the stuff goes back to y2 minus y1 over x2 minus x1. But it just gets closer and closer, and we want the limit of that as that H approaches 0. Okay, then let me show you this guy. Remember last Friday? I don't think anyone liked last Friday, but remember last Friday, we were supposed to plot all the slopes. And then we kind of just said, okay, we're going to do if it's positive slope, negative slope, is it getting closer to 0? This guy actually plots that. It literally is, here's the slope up here. So let's like if I go to -1, I don't know how close I can get, it's actually calculating the slope up here, and it's like 3.77. And so that's what it's plotting. This point here is -1, 3.77. It's literally plotting all the slopes. It's calculating the slope, and then it's plotting it down here. I don't know if you can see, but this is like -1. So do you see how why this is at the bottom? This is -1. Look, actually, can I go back? Where should I be? Oh, let's just keep going on. Oh, what am I? This guy right here. Where should I be when I'm at the bottom there? On the derivative, this is the graph of the derivative, I better be at 0, right? And then when I start up again, I'm going to have positive slope, right? If I drew a tangent line in here, this would be positive. So as I keep going, notice down here, I'm going to be going positive. Okay. I hit here, I'm back to 0. Okay. This doesn't really mean anything. Where the graph hits, that might be where it changes from, that might be what's called a point of inflection, but in general, it doesn't mean anything when the graph hits 0. And then as I come down here, see how I'm back to 0 again? Remember how we were doing that last Friday? Did everyone tune out? Okay. But here's what I want to show you on this without actually doing a proof, and then I'll let you go. Let's do the same thing for sine. What is the derivative of sine? Cosine. Does anyone know what the cosine wave looks like? If not, let's plot all these slopes. I'll animate it so I'll go faster. If I plot all these slopes, what is that green down there? Remember, it's plotting every single slope. And when you plot every single slope, that green, the derivative, is actually the cosine wave. Okay, so I didn't show you as a proof. Well, I'll let you get out early today, but at least, well, I'm still going to say that. I still want to get to that, but at least you could see it visually, right? You could at least see that visually. Let me see if I can reset it. Remember, the bottom is plotting all these slopes, okay? And if we plot all those slopes, it turns into cosine. And if we plot all the cosines, it would actually produce the negative sine wave, which is the sine wave flipped over. Okay. All right, so we'll still get to the proofs, but at least you have a visual. Okay, a little something. That's pretty cool. That's what math teachers think is cool, guys. So where are my math teachers? You better think that's cool. All right, guys. So you have, and I know it's harder for you guys to see in the back, but hopefully you can kind of at least see how it was plotting stuff. Okay, so there's some homework on WebAssign. Okay, and then, like I said, we will have a couple review days next week, so hopefully we'll kind of make sure that we all feel comfortable. All right, have a good weekend, guys. Have a good weekend.